In Chapter 15, we'll be looking at acids and bases, definitions, properties, calculations, and those reactions that happen in equilibrium. Acid-base reactions are a critical component of biological systems and water chemistry. So we'll start with an application related to biological systems, specifically to hemoglobin and carrying of oxygen and carbon dioxide. One of the blood buffering components is carbonic acid. Carbonic acid is H2CO3, and it will exist in equilibrium with carbon dioxide and water. We also see an equilibrium reaction with its acid-base properties, forming H positive, AQ, plus bicarbonate, HCO3 negative, AQ. And both are important to the way the body handles and maintains pH. But also how CO2 is processed and removed. As a part of normal metabolism, sugars, amino acids, and fats will ultimately be converted to carbon dioxide and water. So there has to be some mechanism for getting rid of the carbon dioxide. The problem with elevating the amount of carbon dioxide that there is, or increasing, let's think about Le Chatelier's principle again. Rewrite this equilibrium. Carbon dioxide plus water. Okay, so as carbon dioxide increases, the equilibrium will shift to the left to make more of the carbonic acid. And so H2CO3 will also increase. Ultimately, what happens, and we'll talk more about the reason for this, pH will decrease. Right? So at some point, that carbon dioxide has to be removed. One of the ways that this happens is through bicarbonate. Okay, we've already said that this will be in equilibrium also with hydronium plus HCO3 bicarbonate. And this bicarbonate goes back with hemoglobin after oxygen has been removed, after the O2 is released, to the lungs, where the CO2, from the reaction, this will produce CO2 in water. The CO2 will be released and exhaled. Right, so going back and thinking about pH for just a minute, it is very important that blood maintains a consistent pH. pH of 7.42 on average. So any deviation from that, either higher or lower, can cause a problem. And we'll talk more about what the effect can be in a person and how they might have problems with CO2 metabolism. The first thing that we need to do is define some terms that I have already been using. Hydronium is a hydrogen ion, specifically H positive. Sometimes it's called a proton. If you think about it, because hydrogen has one electron and one proton, if the electron has been removed, all that remains is the proton. We could also write this as H3O positive, and that goes back to this hydronium would be in a water-based system, if we're talking specifically about pH. So a lot of times it would be written as H3O positive. And the Lewis structure, which we've drawn before, looks something like that. All right, so let me erase there for a second. And go to the next term. Hydroxide is the ion OH negative 1. And so the Lewis structure of this particular ion would look like that, with the oxygen having the lone pair. And so typically, if you think about it, when water breaks down into its component ions, we would get H positive plus OH negative. So these two things are made from the dissociation of water. There are two different common definitions for acids and bases. The first is the Arrhenius acid. This is defined as a compound which reacts to produce hydronium in aqueous solutions. Right, the second term related to that is the Arrhenius base, and this is defined as a compound I could say the same thing, which reacts to produce, in this case, hydroxides in solution. A different type of definition for acid and base are Bronsted-Lowry. And the Bronsted-Lowry definition says that an acid is a compound which donates hydronium. And a Bronsted-Lowry base is a compound which accepts hydronium. And so we'll see cases where either the Arrhenius acid-base definition or the Bronsted-Lowry acid-base definition works better, and some which are more applicable. It really just depends on the type of chemistry that you're doing. Now that we've defined what an acid is, let's talk about some general properties of acids. We see acids in a lot of different foods, especially citrus and peppers. really many different types of fruits and vegetables. So the first property is that they're components in many different foods. Number 2, they taste sour. That makes sense. If you think about a lemon or a lime, grapefruit, they taste sour. And a lot of people prefer this sort of taste in their candy, or they like hot. I'm trying to think of the best word. I guess caustic maybe is the term we use. I don't know if that's the best term, but it's the kind of food or drink that causes that prickling sensation. And you think about sodas, in those cases, in particular, they contain carbonic acid. So that fizz that you get, or the prickling sensation, comes from the carbonic acid, which is acidic, of course. Number 3 is they produce low pH solutions. So an acidic solution would be anything that is less than 7, a pH of 7. So 7, less than 7 is acidic. We also know that they turn litmus paper pink. Most typically, the kind of litmus we use is pink already, so they just stay the same color. All right, we can look at the properties of bases in contrast. We see these in a lot of cleaning solutions as compared to foods. If you look at the picture on the right there, you see all different kinds of cleaning solutions: Comet, ammonia, Drano, Easy Off. And related to that, bases are used in soap making. So they will appear to be soapy. Number 3, they react with acids to make neutral solutions. Number 4, they produce solutions that have high pHs. So a basic solution would be anything greater than 7. And number 5, they turn litmus paper blue. There are 3 general types of acids. Let me list them here, and then we'll talk about them in more detail. The halogens, and this would be like HCl. Acids made from polyatomic ions. And this would be like sulfuric acid, H2SO4. And number 3, organic acids. We can also talk about strong and weak acids. Strong acids would include HCl, H2SO4, and several more. The weak acids would include all of the organic acids. And then some of those in the other 2 categories. The difference between strong versus weak is a matter of the amount of ionization. Whoops, let me erase that. amount of ionization. In other words, how complete the reaction is. So a strong acid will completely ionize. There is no equilibrium. And a weak acid will exist in some sort of equilibrium. What that equilibrium looks like really just depends on the acid. We can also look at the list here, and you can see what things are used for. Hydrochloric acid, which is a strong acid, and I'll just put SA here. Metal cleaning, food preparation, component of stomach acid. Sulfuric acid is also a strong acid, as I've mentioned. Fertilizer and explosives, dye, glue, automobile batteries, electroplating of copper. Nitric acid, which is also a strong acid. Fertilizer, explosives, dye, and glue. So you see some common threads between them. And the others on the list are all weak acids. Okay, so I'll just do like that. Even though some of them may still be used for things like metal cleaning or fertilizer manufacture, it's just a different degree. Right, our first category are the acids that are made from halogens. And the way that we name these is to say hydro, then the root of the halogen, ic acid. So HF becomes hydrofluoric. Ic acid, hydrofluoric acid. HCl is hydrochloric. HBr is hydrobromic. And lastly is hydroiodic. So looking at this chart, as we move down the chart and to the right, so here, actually, let me use a different color. The hydroiodic, hydrobromic, as we go down, the acids become stronger. And as a matter of fact, we don't even keep these really in the stock room because of the strength of the acid. The only one on the list of those, HF, hydrofluoric acid, is a weak acid. We use hydrochloric acid all of the time in the laboratory. It's one of the most common acids that we use for routine laboratory work. The acids that come from polyatomic ions, there is a root ion. So we can start with the most common ones. See if I can think of any others. Okay, so the name of these ions, NO3 is nitrate, SO4 is sulfate, whoops, okay, so let me just write that, sulfate, this is phosphate, and carbonate. The way that we name these acids is the root of the polyatomic ion, ic acid. So the first one becomes, acid shows the hydronium with it. And the name of this one is nitric acid. Second one is H2SO4. This is sulfuric acid. H3PO4 is phosphoric. And you may say, how do I know if it's H2 or H3? And the way you know is from the charge. Okay, so we need a proton for each of those negative charges, or a positive charge for each negative, in order to balance it out and neutralize the ion. And the last one, H2CO3, is carbonic acid, as I've already mentioned on this video. Nitric and sulfuric are strong acids. Phosphoric and carbonic are weak acids. There's an additional component to this. We also have the ions that are made from one less oxygen. Okay, and so the name of this ion, NO2 -1, is nitrite. And then sulfite and phosphite. And so when we name these, they become the root OUS acid. Okay, so same thing again. We write the proton with it. HNO2 becomes nitrous acid. H2SO3 becomes sulfurous acid. And H3PO3, phosphorus. Okay, I'm going to see if I can move this up just a little bit. There's a couple of more terms that I need to define. Diprotic and polyprotic. A diprotic acid is an acid with 2 hydronium. So an example of this would be H2SO4. And what that means is that it can undergo 2 acid-base reactions. A polyprotic acid is an acid with 3 hydronium or more, technically could be. An example would be phosphoric acid, H3PO4. And so in this case, be one reaction per hydronium. So this would go through, phosphoric acid would go through 3 acid-base reaction. It becomes important when we start talking about buffers and biological systems, so we'll talk more about that in Chapter 16. Organic acids are acids made from carbon, specifically hydrocarbons. They have common names. You'll learn more about them in organic chemistry if you take that course. And they all have a carboxylic acid functional group. Which looks like this: a carbon with a double bond, 1 oxygen, and then attached to another oxygen. And so this hydrogen right here that is attached to that oxygen is the acid base reacting hydrogen. The 2 most common organic acids, I'll just draw the structural formula here. This is acetic acid. And it's the major component in what we know as vinegar. The second most common one is this one. Has one less carbon, and it's called formic acid. And we know this in ant venom stings. We'll talk more about organic acids later, particularly with those that are in equilibrium, equilibrium reactions. And these are also weak acids. Here's a list of some common bases. All soluble hydroxides, okay, soluble being the key word there, are strong bases. And we just name these the metal and hydroxide. So you see something like MgOH2 as magnesium hydroxide. Otherwise, the other bases shown here are all weak bases. Sodium bicarbonate, sodium carbonate, and ammonia. You will see a lot of weak bases that have nitrogen as a primary component, especially when we're talking about organic bases. Lastly, in section 1, we're going to look at 4 compounds and classify them as, first, we'll classify them as an acid or a base. And then number 2, we'll write a chemical reaction showing how it reacts. So write a reaction. And we've got 4 different compounds. HNO3, NH4 with a positive 1 charge, potassium hydroxide, it's letter C, and letter D is HC2, whoa, let me erase that. Well, it's not letting me erase, so I'll just write, just put a line through that and put HC2, H3O2. Okay, so first, HNO3, this is an acid. This is nitric acid. And I know that from just referencing my list. Letter B, NH4. This one, you're shown that NH3 is the base. NH4, and we'll see this is true for other positively or cation compounds, they are acids. Letter C, potassium hydroxide is a base. And letter D, HCTH3O2, C2H3O2. This is an acid. This is an acetic acid. That's just a different way to write that. Another way you can look at it is, going ahead and drawing out the compound. That's 1 carbon, and then there's another carbon. Remember that each carbon has to have 4 covalent bonds, and it helps you arrange it a little bit when you write it out like that. Okay, so let's write our reactions. Let me erase for a minute. Okay, and I'll rewrite HC2, H3O2. Okay, so our first one, HNO3, will react to produce hydronium This is AQ plus nitrate. And all I have to do is go back and look at that polyatomic ion to know what the other product will be. The way you can kind of think about it, if I'm looking at something like HCl, remember that's the same thing as writing the Lewis structure like that, showing the two dots shared between them. So what happens is, because chlorine is so much more electronegative, both of those electrons will go with chlorine, and so hydrogen is left without. It becomes hydrogen +1, and the chlorine becomes chloride -1. Right, my second reaction here, NH4, I said it would react as an acid. Okay, so we're just going to pull one of those hydrogen off. When we do that, the positive charge goes with it. Okay, so we have NH3 plus hydronium. We know if it's an acid that hydronium is always going to be one of the products, because that is the definition. All right, the next one, potassium hydroxide reacts as a base. So we're just going to separate that into the components, potassium plus hydroxide. It makes hydroxide in solution. Okay, and lastly, HC2H3O2. And we're always going to look at the hydrogen that's by itself. That's the one that is going to be removed. So we get C2H3O2 negative. Remember, the electron stays behind, plus hydronium. You'll have some examples like this in class to practice on writing acid-base equations. And then we'll go to calculations next.